Welcome back. Let's just give everyone a few minutes to join and then we can get started. Hope you all had a great weekend. It's amazing, but we are already in the last week of the program. Today, we're going to talk about the intersection between quantum computing and high performance computing. This is going to be a fun session where we're going to talk about how we can integrate quantum algorithms into existing HPC workflows. Where are there opportunities for the synergies between the two? And what does the future really hold for quantum technology as it matures? Our moderator for today's fireside chat, we have with us Ricky Young. Ricky is the COO of Qbraid, a quantum computing startup building a one-stop shop for quantum computing software and hardware. And before joining Qbraid, Ricky worked at AudioShake AI and worked as a software engineer for Japan's largest social media platform. And Ricky grew up in Michigan and graduated from Stanford with a BS in engineering physics with a focus on quantum science. Over to you, Ricky.
We're going to provide the opportunity for everyone to ask any questions. We will also field a few questions as well. So don't be shy. We'd love to hear from you, as well as all the thoughts that you may have around what is going to be a very exciting session, but also a very exciting part of quantum computing and quantum information, as many countries such as Japan, United States, many countries in Europe, and even some smaller players in quantum such as Indonesia begin to start to build HPC centers with allocations or intentions to add in quantum computers for various research from quantum error correction, as well as for the hybrid compute workflows that Abhinay just mentioned. So just to begin with a speaker bio, Sara Marzella is the quantum computing and HPC specialist at CINECA. CINECA is the Italian HPC Center initiative. Is that correct, Sara? Okay, great. And Sara holds a bachelor's degree in applied mathematics from La Sapienza, University of Rome, and a master's degree from Bicocca, University of Milan, where she specialized in machine learning before transitioning to quantum computing. Today, Sara is part of the Quantum Computing Lab at CINECA, where she focuses on the integration, application, and outreach of hybrid HPC QC systems with a passion for making complex scientific concepts accessible. Sara is very deeply involved in science communication, helping to bridge the gap between cutting-edge research and public understanding. Next, we have Dr. Travis Humble, who is the Director of Quantum Science Center at Oak Ridge National Laboratory. Dr. Humble is Director of the Department of Energy's Quantum Science Center, a distinguished scientist at Oak Ridge National Laboratory, and Director of the lab's Quantum Computing Institute. Travis leads the development of new quantum technologies and infrastructure to impact the DOE's mission of scientific discovery. Dr. Humble is also Editor-in-Chief for ACM Transactions on Quantum Computing and co-chair of the IEEE Quantum Initiative. Dr. Humble holds a joint faculty appointment with the University of Tennessee Bradenson Center. Is that also correct? Should have checked these. Okay, for interdisciplinary research and graduate education to work with students in developing energy-efficient computing solutions. Travis received a doctorate in theoretical chemistry from the University of Oregon before joining Oak Ridge in 2005. Alrighty, so to kick it off, I'd love to ask each of you guys a overall question about what exactly differs in your guys' perspective of quantum HPC and HPC. So Travis, I think you're unmuted, so would you mind going first? And then maybe we can have Sara answer as well.
Of course, Ricky, and thank you for the opportunity. It's a pleasure to be here on the panel. I do think that quantum computing is fundamentally different from high-performance computing. And by putting these two things together, we can create something that we've never seen before. I am personally excited about all of the opportunities to use quantum computers for simulating new types of physics and physical sciences, but then also combining that with high-performance computing so that we can accelerate workflows that, frankly, we have already become dependent on, including artificial intelligence, machine learning, modeling and simulation, all of these types of topics. So for me, the opening line here would really be that it is fundamentally different, but only by putting these two things together can we really get something more powerful that makes a big impact on what we're trying to accomplish.
I completely agree with Travis. And indeed, at the beginning of quantum computing, we didn't think to put it with HPC because they are two completely different paradigms. But we are start thinking about a new evolution of quantum computing and of HPC and putting together in some way, but the projects are just at the beginning and we still don't have any, or we have very few hybrid algorithms that are really HPC quantum hybrid, because having an algorithm that is able to exploit quantum capabilities, and HPC capabilities, so the multi-CPU programming, the GPU programming, is something that still doesn't exist. And we are really excited on working on this new frontier.
Fantastic. I think just to add on to some of the differences and to provide some color to the difference between quantum HPC and HPC, one of the questions that I have is also the different modalities of quantum computers can also differ the approach of HPCs. And maybe we can, I would love to know more about, how you guys consider adding in different infrastructure or different architectures specifically, and what are the considerations you have to make, as well as if each of you could answer that, that would be great.
Yes, so I can start maybe talking about the first problem that we are facing in integration between HPC and quantum computers. As you probably know, or you can you can check, we are buying two different types of quantum computers in CINECA. One is a superconducting and one is a neutral atom quantum computer. And they obviously work in different ways, but they have different times for running a job, but they really different times. So if we are talking about a superconducting quantum computer, we have a job that runs in few seconds or a few minutes. Instead, for a neutral atom quantum computer, we can have a range of 30 minutes or more. And this means that we have to schedule a workflow in different way between the two quantum computers, because if we use the same approach for the two of them, we have we lose some resources, because if we just take the resources of HPC waiting, meanwhile the job is running on the quantum computer, thinking about a superconducting quantum computer, everything works fine, because in a few seconds we have our response back and we can start again using our HPC resources. But if we do the same with a neutral atom quantum computer, what happens is that if the job requires half an hour, we have the CPUs or the GPUs waiting for half an hour, and it could be quite a waste of time and resources, and vice versa. If we have the CPU, the QPU that is waiting, meanwhile the HPC resources are running, our waste of resources can be different if we are talking of a superconducting quantum computer or a neutral atom quantum computer or something else. So we are trying to find a way to make them interact in a easy way for the users, but it's hard to find the same way between the two type of quantum computers. And then another important point is the vendor specific implementations that are different between the quantum computers. Each vendors allows you to have a different level of abstraction and access to low level information. And this implies a different way to integrate quantum computer with the HPC. We are trying to work on a standardization with the vendors and with all the research labs and computing labs around Europe and the world. But yes, we are just at the first steps. I don't know, Travis, if you have more points. There are more points.
Of course, like Sara was saying, quantum computing fundamentally stores and processes information using quantum mechanics. And there are many different systems that are available for doing this. The superconducting circuits, the trapped ions, the neutral atoms are just a few. Each of those systems has unique physical properties about that. The timescales on which they operate, the energy that it takes to perform those operations, and then also the types of instruments and infrastructure that you need in order to build those types of systems. I would say that today is still very early in the development of quantum computing technology, both in terms of the infrastructure, which we want to make those types of systems, and then also our understanding and the performance and its improvement. But it's not too early to start thinking about how do the different technologies behave and how would we make use of them in a bigger high-performance computing system. I give you one specific example. One of the technologies, let's say superconducting transmons, they use a dilution refrigerator. It's a very big piece of equipment. It reduces the materials down to millikelvin temperatures, and so that they can have their quantum coherence. The problem, though, is that that piece of equipment can be very sensitive to vibrations, electromagnetic interference, other sources of environmental disturbances. And many HPC centers are filled with environmental disturbances. They are complex, noisy operation facilities, and understanding how those technologies, those quantum technologies, could be put into a facility that has all of those sources of noise, that's an important question that we can start thinking about today. So I think all of these different technologies deserves our attention because there may be different opportunities for their integration into HPC environments that, again, like Sara was saying, takes advantage of the physics and the properties of those physics in unique ways.
Awesome. Thank you very much. I think one question that also sparks my mind is if, in the case of the current landscape for quantum algorithms that are, and in the pursuit of like applications for quantum computing, one of the bottlenecks has been to actually have a quantum computer that you can actually do more, actually test algorithms and stuff. So how can you guys kind of illustrate to me how exactly the roadmap would be to kind of get to that stage? Because it's not, I understand from what Travis told us, is it's not just about just putting a computer there. There's a lot of other considerations. What are maybe some of like the first steps that are being taken both at your respective organizations to finally get to a point where we can test an algorithm fully using this kind of infrastructure? Sara, go for it.
Okay. So as you were saying, this is an evolving topic and it's difficult to make precise predictions at this stage. We have several projects that are trying to approach this problem in different ways. One of them is the HPC integration project, and one of the scopes of this project is to build libraries for testing these hybrid algorithms, so shared libraries that we can use to benchmark and to test these integrations, because we still haven't do that. So we're starting drawing some examples and some ideas using the emulators. Likely we have the quantum emulators. So these are the algorithms libraries that emulates the behavior of a quantum machine on a classical machine, so they can tell us the exact result that we expect from a quantum machine. And we can use them to do this simulation of an algorithm and try to figure out some benchmark. But it is just the first step, and then we will need to test it on the real machines and to check with different machines. Even understanding which machine is better for which application is not that easy. We have some ideas, as you probably know. Some machines are better for optimization or simulations or machine learning, but we still have to build a complex system that can benchmark them and to have a complete overview on how this synergy between HPC and quantum computing can work.
I completely agree with this answer in the sense that it's very open right now, the question of what's the best way to use a quantum computer to solve a problem. The development of algorithms and the applications of those algorithms is all, I would say, current research. There have been a few really good examples. In fact, even one of the first examples to motivate quantum computing was the idea that a quantum computer could simulate Schrodinger's equation, this fundamental equation from quantum mechanics, which would allow you to model chemistry and physics and materials and all of these things. It's a beautiful idea, but it turns out doing it is much more difficult than saying it. The types of performance that you need in the quantum computer, the quality of the qubits, the quality of the gates, the depth of the circuit, the complexity of the algorithm itself, all of these pieces are things that we're now starting to learn about. But there's also another question related to this. It's the benchmarking that Sara mentioned. When does the quantum computer start to become advantageous to use for these applications? And this gets to the roadmap, Ricky. I think you were asking about what's the timeline before we develop a quantum computer that solves a problem we could not have solved with any other approach? This is something at Oak Ridge we've been thinking about a lot. We have one of the world's fastest supercomputers, and we often use that as a point of comparison to quantum computers. When could a quantum computer outperform the supercomputer? We've had a few examples working with Google, with JP Morgan Chase, and different industry providers on using quantum computers and comparing directly with the supercomputer. They're fun. They're fun examples. They're fun tests. It's always exciting to see what's going to happen. I would personally say the quantum computer and the HPC are very close right now. It's difficult to say who's actually in front. But I don't think that that's really the best way to think about the quantum computer. I think we have to imagine the quantum computer and the HPC system working together on a problem that neither of them can solve well by themselves. And this is a very open space. And we're still now just trying to understand, is it the hybrid algorithm Sara's talking about? Is it some sort of streaming workflow or iterative design? All of these are really great questions. But this is exactly where we are today, and the roadmap for how long it takes to get to a system development where the quantum HPC is the most powerful supercomputer in the world. People are saying 5 to 10 years, but honestly, it's anyone's guess at this stage because it requires a lot of really creative research to understand how to mix these paradigms together.
Yes, that is, I think, what's to me quite exciting about this quantum HPC is just how open it is right now with so many ideas that can be implemented, tested out. Could you kind of illustrate a little bit more about how exactly, apart from like quantum simulation, like having a quantum HPC center could help with improving quantum computing itself? Maybe there are some ideas there that you could maybe expound on.
I can certainly give you a few examples that I think about a lot. And right now with the quantum computing vendors, and these are all the companies developing quantum computing systems, many academic laboratories develop quantum computers as well. We do this at Oak Ridge too. The question of how you get access to the quantum computer, is it a experiment or is it a computer? This is sometimes a blurred definition. Oftentimes, we are using remote access or cloud access models to develop on these systems. Of course, that's a little different from how we think about HPC systems, which are often more physically closely integrated. There's a lot going on, I think, in cloud computing that maybe is shifting that paradigm. In addition, the tools and software and the workflow that you need to develop to, one, make those systems accessible. That's another really hot area of research. What's the language that you should use to program a quantum computer? And is that language compatible with your high performance computing system? That actually turns out to be not so easy. The answer is not Python, by the way. There has to be something maybe a little more efficient in there. What are the architectures when you put these systems together? Is it one quantum computer and many nodes in a high performance computing system? Or does every node in a HPC system get a QPU just like it gets a GPU? These are questions that have very different trade-offs and optimizations to them. It's certainly the type of research that we like to do at Oak Ridge, and I think many other places are doing it as well. Sara, maybe I turn it over to you to comment on this too.
Oh, yes. I was thinking about how can HPC be helpful for quantum computing and in this iteration. And one thing is that what I'm seeing is that HPC centers are like, or National Laboratory are like a connection between the quantum vendors and quantum developers and the users. Because right now, a lot of companies have done a lot of work in trying to keep in touch with users and doing education and those things that are really, really useful. But maybe there is a little bit of gap with the research users, or at least the research users that uses HPC systems. And we are trying to build this link that is hard to, because we cannot expect that users know about programming with C or Fortran or some other language that is for HPC, programming in a parallel way, programming from quantum computer, maybe different types of quantum computers, and all these. And then the argument, their topic that they of their research, because they probably are not researching about HPC. They are chemical or something like that, chemicists, and so they need too many skills, and trying to find the right trade-off on how complex this integration should be to be more efficient as possible. But it has to be even at the level of the users, because it is completely not useful if no one can use it. Is another big challenge that we are facing with quantum computer vendors and developers.
I want to just emphasize this point, if it's okay, that the need to have people adopt a technology is incredibly important to its life cycle. Think of all the good ideas that nobody adopted. And the truth is, it's difficult because we don't remember them, because they disappeared from history. And in this case, quantum computing, the efforts that we're going on right now are partly to increase that adoption and awareness of the technology, because I think that only if people start to understand the impact that it can have, and like Sara was saying, it's accessible to them so that they can use it, only then will we start to see that impact actually happen.
Yes, that's true. We can think about GPUs, for example. At the beginning, no one cared about GPUs, but then we found the right application and the right way to implement them in a synergic way with all the HPC system. And so they knew a new golden era. Or even the machine learning and the AI. Machine learning exists from decades, but it's living its golden era right now because it's easy to use, because someone brought the AI to the all the users, but there is, say, a higher or a deeper way to use machine learning and AI, and not all the users can do that. But if we want to bring the technology to a new era, we have to put our effort, and the users have to, to put their effort on this evolution.
I
Completely
really
agree.
love that. What's great is it's almost like it's always phrased as like a chicken or the egg problem, right? It's like you got to have the application first to do what you want to do, but then if you don't have all the work done to actually even build the application, then nothing will happen. But what it seems like is we actually answered this in a different way, where the sustained efforts in very multidisciplinary facets will help out with eventually getting towards an application, which will hopefully just catalyze it even further. So that's, I think, really, really good to hear, because sometimes it can, when you're always in the trenches, it's like, okay, is something going to happen? And it's not always sure as to whether you're going to have like an application in the future, but it's a team effort, it sounds like, where everyone across the world is working on different facets and different aspects. I'd like to circle back to that real quickly at the end about how people can get started in doing research here, but in adding additional color, not just on the software side of linking, Fortran or Slurm, as well as what are some of like the hardware side? I know, Sara, I don't know if the computer is quite there in the facility yet, but there's noise concerns, heat concerns, even like an idea of having to put lab space next to it because you have to calibrate the quantum computer. What are some of these considerations that have to be made?
Yes, so it depends from the quantum computer where they run Right now, they are building the IQM quantum computer inside Technopole in Bologna, and the other one instead will be delivered at the end of this year. We have two different approaches on the hardware support for these computers. It depends from the vendor and from the system, because some systems have more complex calibrations or more longer calibrations, and is really hard, really complex to find the right solution, site solution. As Travis was saying before, installing a quantum computer is such a sensitive machine inside an HPC center that is very noisy. There has a lot of heat, and instead, quantum computers usually needs low temperatures. Or at least even 25 Celsius degree is a low temperature for an HPC system. And so it's a really a huge problem, and it's a challenge that we are facing right now. I don't know if I'm missing something, maybe the first part of the question, but maybe Travis can.
Yeah.
Sarah, I completely agree. The other piece I was going to add to that is that the expertise that you need to address those problems in the HPC center oftentimes is not there already. Certainly, people are present who are engineers and systems managers, facility operators, and they will understand what are the power consumptions and the water requirements and cooling requirements that a new technology will need. But certainly at Oak Ridge, what we find is that when people hear you have lasers or you have a rare chemical that's going to be included, or maybe there's concern about magnetic fields, that's entirely new types of considerations that we have to get comfortable with. And we need people who have the expertise and the knowledge, both from operations, but also from safety, to make sure that these systems can be safe and secure and operate well. So I think I agree strongly with all of the points you made. We also need to develop the skills and the people. And Ricky, it sounds like we'll come back to that later, but I would just emphasize that that's another challenge to establish these types of quantum HPC centers.
Yes, we're facing the same problem.
Lots of challenges, but that's what's exciting, right? Everything from like workforce development to even finding the lab space, even getting like a quantum computer in there, to even thinking about the whole pipeline, getting application scientists involved as well. That's very, very cool. I'm going to now switch to some of the fielded questions. We have one from Hussein. I'm going to modify this one a little to tie into what Travis just talked about with regards to energy consumption, as well as some of like the more exotic research, as well as the application side of having to put in lasers into an HPC center for controlling the atoms, for example. But his question was, if you were to use an HPC, wouldn't it increase the cost to millions of dollars, since you have to use big classical computers? And if it's so expensive due to electricity, what are perhaps some of the other considerations when you're using a quantum computer that do incur costs as well? So from a cost perspective, how does it all play out?
So if I understand this question, there's maybe a couple ways to look at it. One is, what are the costs that we expect to install and operate a quantum computer? And in this sense, I think it's very similar to our high performance computing systems. There, of course, is the procurement, the purchasing of the actual equipment, as well as the installation. You might have to modify your building to host that equipment, just like we were talking about. Then, of course, what are the utilities, the electricity, the power, the water, other types of utilities that you need to operate that system? And I would say that at the moment, the current quantum computers are very small scale compared to high performance computing systems. That is not even really a noticeable comparison. The quantum computing systems that you can get today on the market, they may use at most a few hundred kilowatts of power. The the HPC system that we have at Oak Ridge, just one of them uses 20 megawatts of power. So these are vastly different energy scales. And so from that perspective, today's quantum computers are still prototypes, and they're not yet at the large scale where I worry about the cost of operating them. But when they do get bigger, and this could be 5-10 years like we were talking about, then there are concerns that the quantum computer itself may have energy requirements that make the value of operating that system less. But there are some technical reasons why that may not be true. One, the amount of energy it takes to perform a quantum operation on a single particle is in some sense the smallest amount of energy that you could ever hope for, about 1,000 times less energy per operation than conventional semiconductor CMOS technology. So that's one advantage. The second advantage is that the number of operations that you do in the quantum computer actually can be many orders of magnitude less than the operations required on the HPC system. So you get two factors now that multiply together. I have fewer operations and each operation costs less. But the things working against it are, well, if I have to use a high power laser just to have a high probability of that operation occurring, what happened to all the extra energy my laser produced? And there is currently no mechanism for recycling energy within these quantum computers. And for that reason, I think we have a lot of open questions about how the technology develops to be energy efficient going forward. But Ricky, I guess kind of to get to this point about what's the cost, a lot of it's not yet clearly defined, but it's not the thing that I worry most about at the moment.
I completely agree. I will just add a few things about the cost just to give an idea. So I completely agree that an HPC is very expensive, and so it is a quantum computer. So that's why HPC centers and national laboratory are buying these quantum computers, because they're the only entities that usually buy some computer that is so expensive. About the installation, the site preparation, we're facing some cost problem, okay, not a problem, but some challenge that we haven't expected about putting everything in a safe structure, because for some type of quantum computers this can be quite expensive and complex, needs a lot of space and a lot of security systems like interlock doors, special windows, special special walls, and those things. This was quite a challenge for us. About the utilities, the refrigeration system, and the electricity, as you were saying, an HPC center is completely organized for this. For example, in Technopole, if I don't get wrong, we have two different lines of refrigeration, liquid refrigeration system that have two different temperatures, so we can adapt to almost every type of quantum computer, because it's one of the other in the most of the case. Or we have refrigeration with air refrigeration, so that's fine. And an HPC consumes a lot more energy and needs a lot more refrigeration with respect to a quantum computer. And for the perspective in the future, yes, we expect that they will not consume a lot more. Right now, the most of the consumption, the electricity consumption of a quantum computer is given from the refrigeration system and from the CPUs that are inside the quantum computer, leading the communication with the external computer. So one CPU is right now and one CPU will be in the future, and so we are not worried about this.
Awesome. When you guys are also discussing how these are toy or small scale quantum computers, Gamzi also asked a question about how many of these quantum computers have a very high error rate, and is there a way to ensure the accuracy in these hybrid systems, perhaps in a way that's different from if you were to use like a cloud provider and use their instance and then do the orchestration via the cloud? Is there anything that improves or ensures the accuracy of results that are specific to a quantum HPC or unique to it?
I think this is a very nice question, in part because it gets back to the benchmarking that we were talking about a little while ago. How do you measure the performance of a quantum computer? And accuracy is one of those metrics. Does it give me the right answer? And you would think that that should always be a metric. But the truth is there are some algorithms, some applications where getting almost the right answer is okay. Think of optimization. I don't have to be perfectly optimized. I need just to be almost perfectly optimized. That's an okay answer as well. But there are other problems like multiplication where being wrong is unacceptable. You have to actually know that 3 times 5 is 15. 16 is not an acceptable answer, even though it's very close to 15. In this sense, you can design problems, benchmarks, that actually evaluate accuracy from these different perspectives. Some of them can be looking for what is the probability of getting the exactly correct answer. Others can be looking at them as, well, what is the closest that we can get to the optimal answer? And so there's different definitions of accuracy that show up here. But I think the real question about the error rates has to do with how can we mitigate, detect, and correct errors. And this is the sophisticated technology we were talking about earlier. There are actually methods within quantum computing for quantum error correction where if you can reduce the error rate of the devices to a low enough level, then detecting those errors provides you with enough information to actually correct the effect of that error. And at a low enough level, that can become a sustainable correction, what they call fault tolerant. You can tolerate the faults to a certain complexity of your calculation, and that is now a measure of this accuracy as well. We are just at the first stages of demonstrating fault tolerance at very small scales in very early technologies. And in some cases, you might think that the success of quantum computing will depend on our ability to scale up fault tolerance to very large number of qubits and very complex calculations. So I hope that was close. I don't know if that was an exact question or not.
Just wanted to add that I know there are some researchers that are working on hybrid algorithms that allows to do some error correction using the HPC side and then going back to the quantum computer. But right now the problem is that we have a lot of latency. Quantum computers can be connected only via cloud or with an Ethernet cable that has a really high latency connection. And so right now is not feasible in an efficient way, but maybe in the future.
Mhm. So would you guys say that it could be an interesting topic in the future where the HPC could provide some kind of post-measurement error, post-measurement improvements of the results that might be a little bit better than if it were to, for example, be done over the cloud or via the cloud? Is that kind of an idea, or is that something that's like, maybe there isn't too much of a difference between doing something on the cloud and doing something on the HPC to improve the error rates or the performance of a quantum computer?
No, I expect the differences because for the latency, because obviously if you want an efficient algorithm, you want it to run very fast. And if you have to wait for the classical part to send you the optimization of the parameters or the error correction on what it is, and then go back via cloud and then it is a really not efficient way to do a computation.
Mhm. Gotcha.
Yeah, I agree with this as well.
All right. And I think we have a question from Ron Schreiner, and I'm sure many quantum enthusiasts probably have this question because a lot of them use Qiskit, or a lot of them use Python at least. If it's not Python, which programming language should be better? Is it perhaps Rust? Will they even interface with this faster language? Is that necessary? Can they still code in Python and still work with the quantum HPC? Would love to know what would be the interface there for coding.
Ricky, so I feel like I may have walked into this when I made the statement earlier, it's not Python. So, and I probably knew that would get a reaction. When I said this, I didn't mean to dismiss Python. I think Python is a wonderful language, especially for fast prototyping. And this is why I see Qiskit and a lot of the tools that are Pythonic in the quantum ecosystem being very popular. Because as developers, we actually need feedback on how things are working. And Python and the interpreted environment provides a great way of getting that feedback quickly, sharing code. It's relatively easy to understand and learn. So in this sense, it's a great language. The comment, though, was more towards how HPC systems operate as high performance computing systems, where we are much more concerned about system level resource management and latency and other concerns that often Python simply is not worried about. I'm not saying that you couldn't figure out a good way to make Python work, but it's not the natural path for Python as a language to develop. there are many alternatives to this. Rust, of course, is one. C, C++ is very conventional. Sara said Fortran. That's not a joke, right? Because there are actually codes for many decades now that we have ensured continue to operate using Fortran language. And quantum computers may face a similar question about, is there an interface for Fortran at some time? So I think the language question, the high level language question of what does the user program in, is going to depend in part on how do we design these systems and what are the performance expectations we have for how the systems behave. What we are seeing at Oak Ridge is that we want a much faster response, a much tighter integration, much finer control over the resources themselves. And so we're looking at things like C, C++, Rust, and other languages.
Awesome.
Completely agree with this point. Obviously, all the programs for HPC systems are developed for C or Fortran or those types of languages. I heard about Rust too. I don't use it, but I heard that this can be an option for the integration between quantum computers and HPC systems.
If you don't mind me kind of asking a little bit more about this, how would this exactly, like C, C++, interface with the likes of the intermediate representation, such as chasm, for example? Would you still kind of boil it down to like a QIR or a chasm, or are we thinking in a completely different way here, where the quantum computer would be interfacing with these languages in a completely different way?
Yes, there is a discussion on this topic too. Obviously, everything is evolving right now, so we don't have answer to any of these points. But there is a discussion ongoing, even because QIR is really good for quantum computers, but is not really good for HPC systems. Instead, IR is really good for HPC systems, but cannot interface with all the properties of quantum computers, for example, low-level control, pulse controls, and those things. And so probably we will need a new language that can do both the things, probably just an evolution of MIR and QIR. Don't know if you have some other interface language, Travis.
No, I agree with you, Sara. I think I agree certainly on the point that this is all open question right now. Nobody's figured out the final answer. There are lots of tools available for conventional programming, HPC systems or otherwise. And this goes back to the adoption that we were talking about earlier. If you have a program that's 100 lines of code, you're probably okay if you have to rewrite it in a new language or, to target a new hardware platform. But if your code is 100,000 lines, you're not going to do it. You're going to wait for someone to make a tool that allows you to convert into that. And the more that we can take advantage of existing computing, programming infrastructure, including compilers, debuggers, all these things, the better it is for the field of quantum computing. But that's maybe where the challenge comes, because it's not clear that quantum computing is better for making these restrictions on its programming at the early stages. So I feel like right now what we are doing is a little bit of meet in the middle approach, where we try to adopt the HPC to look like quantum, we adopt the quantum to look like HPC, and we hope they don't miss each other completely. So it's more of this kind of strategy right now.
Gotcha. Cool. Thank you, guys. That's very enlightening. I'm very excited just to see perhaps in the future. I know there's new AI languages called Mojo, for example. So maybe in the future there would be a quantum computing one as well that meets in the middle for those requirements. We have a question from Sujal, and I'm just gonna try and parse it first just to make sure I got this right. So, there are HPCs that run classical algorithms, and quantum computers rely on doing the quantum algorithms. So what exactly can you blend with an HPC with a quantum computer? What exactly is like the classical side of things that you'd use with an HPC? And then what exactly would be the quantum component to that algorithm?
I can take a first crack at this. I have a specific example we've been working on at Oak Ridge about the HPC quantum hybrid methodology. It's actually a type of algorithm, hybrid algorithm, that's intended to find the lowest energy of a materials model problem. In this case, imagine you have a material and one of the atoms has been replaced with a different atom. They call that a defect. And there's a model for that system that you can create from physics. Solving that problem in practice is not normally easy because it's a quantum mechanical system and it requires lots of memory in order to model that system accurately. Well, we've been working with our partners at IBM on developing an algorithm that starts off with that model and then performs some sampling. What I mean by that is it prepares a quantum circuit. It does a little bit of a calculation that tries to estimate what are the quantum states that are important for that particular model's dynamics, behaviors, and whatever. Think of this as kind of filtering out the parts of the system that you care about. And once you have that information from the quantum computer, you use that reduced amount of states, in this case, the description of the model, to make an effective model that the high performance computer can actually now diagonalize. Still very expensive on the high performance computer, but it's much cheaper, less expensive, less time to diagonalize the smaller model. So by putting those two together, you can actually very quickly determine this smaller effective model and then use the HPC in order to solve the full system. That is a hybrid algorithm we're using right now where there does have to be a strong connection between the two types.
We'll tell about another example about optimization algorithms. So, for example, we had this project in which we wanted to use quantum annealer to solve an optimization problem. When you have the QB formulation, we have lots of parameters, hyperparameters, and you have to optimize them. The machine, the quantum annealer, cannot optimize them if the problem is you have to give the right parameters to the machine, and it could be quite expensive to run it a lot of times to do the fine tuning of the parameters. But you can do the fine tuning using the HPC system and then give the same parameters to the quantum annealer. There are lots of different ways to use them together. For example, fine tuning or the optimization or the post-processing and pre-processing of the data, or otherwise the quantum computer can help the HPC, for example, in machine learning algorithms, or as Travis was saying. But yes, it is still an open question because we have few really good examples and really good algorithms of this interaction. So it's an open question, and if you want to to find the new algorithms and use cases, you're more than welcome.
Nice. So we have like some annealing that works alongside an HPC, and we also have superconducting that also works alongside the HPC. And with that, I want to segue into Cheryl's question, which is a very good naive assumption, is the GPUs, which are based off of CUDA, housed in HPC centers, and quantum computers both work with matrices at the hardware level. So does that actually make it easier to transfer data between the two, or is it just fundamentally just how the bits are stored that make it a bigger problem when you are working these two machines together and trying to transfer data between the two? So what's the data transfer process like?
Yeah, so I think even before you can transfer the data, you have to get the data into the system. And so this is the input or the I/O problem that quantum computers have. And I say problem because it's not fast to initialize a quantum computer with classical data. If I have, let's say, a string of bits that I want to load into my quantum computer's register, whatever technology it is, that process is almost always 100 to 1,000 times slower than actually doing calculations with that system. And this necessarily introduces a bottleneck in the process of loading information into the quantum computer. So the question of how would you have a quantum computer and a classical computer that could be a GPU as well talk to each other, you immediately run into this I/O issue. But in addition to that, the quantum computers are very good at storing superposition of quantum states. If what you really want to store is a specific classical string of bits, then your classical computers are really the best approach for that. So if you're doing matrix multiplication between a matrix A and a matrix B, and you know these are exactly the matrices you want, it's unlikely that your quantum computer can go faster than your GPU. But if the input data needs to be put in superposition, needs to evolve, needs to perform some quantum aspect of its calculation, then you will have to go through this input-output I/O challenge in order to load that data in there. And at the moment, there is really no good way to circumvent this type of problem that we know
of.
Completely.
Sarah, do you have it? Would you like to comment as well?
No, completely agree, and this is the point.
Okay. We do
It's
have
that bad of a problem, Ricky.
yeah. I can see this is, I think, where I've seen the input-output problem and the input I/O problem everywhere. So I can totally get how it's still very much an active area of research. Where Cheryl wants to clarify, and we have two more questions after this. So Cheryl just wanted to clarify, is the main idea for quantum's advantage like the memory space? And if so, could advances in classical memory or some type of quantum memory chip be a better solution than quantum processors?
I think I understand the heart of the question, which is where does the advantage from quantum computing come from? And we had just talked about superposition, which is one of the places we think the advantage comes from, but it's not the only one. And there is actually a familiar trade-off in computing between what they would call memory or space, the amount of storage that you have for data, and time, how long it takes to process that. And in this case, the quantum computer, because it can store things in superposition, is giving you some advantages relative to the amount of time it takes. This is where people make the analogy that the quantum computer solves all problems in parallel, which is cringy to say, so I don't recommend it, but it is the same related argument that is a space or memory advantage. But it's not the only advantage by any measure. There's many others where even with small amount of space and short amount of time, we think quantum computers can have advantage. So I wouldn't say that alone would solve the problem.
Yes. Maybe one thing that I would like to add, that I don't know if this was the one of the thing that can give this doubt about the memory, is when we do emulation about quantum computer behaviors. If we want to do a to perform a quantum algorithm on an HPC, we have to do it in the exact way. So we think about quantum gate circuit, and the gates matrices, and the states are vectors, and we have to multiply matrices by vectors to do the emulation, just in this way, just as you do it during the course, just multiplying matrices and vectors. And GPUs are really, really good and really, really fast in this, but they have very small memories. GPUs have bigger memories, but are and they take more time to do these calculations. But anyway, as you probably have seen, these matrices grow very quickly. As soon as you add more qubits, you have very huge matrices. And so the memory that we have on our HPC is not enough to emulate more than 100 of qubits if we have very few entanglement and we can short these matrices. Right? They can be, the limit can be 20, 30 qubit. We have a very high level of entanglement. So 30 qubit are really few qubits to do some quantum computation. We are talking about logically perfect qubits in this case. So we expect that quantum machines can have more than 30 perfect qubits. So we can compute quantum computation with actual qubits more than 30 qubits. I don't know.
Awesome.
Probably it was quite confused. Sorry, but I hope that the concept to give an idea of the concept.
Yeah, I think it was very clear. So we have maybe 15 to 12 seconds left.
Sorry.
So the last question we have is, how can early career researchers get involved, perhaps on some of like the near-term challenges that you guys are working on, which there appears to be some very exciting ones and lots of them, and both in terms of hardware and software. And maybe you guys can show, if time permits, some of the resources you guys have available. And Katie, maybe we can send it after as well to the audience.
Sarah, would you like to go first?
So the resources of CINECA are shared on the canvas. I think it will take quite a long to show them, but you can find all the information there. And if you need more information, you can write to us. We are trying to be very active on the socials, for example, LinkedIn. So if we launch some challenge, you can find over there, but yes, we don't have. Yes, and you can find the link in the canvas of our CINECA Academy, but we still don't have a lot of courses about quantum computing. We have a lot of courses about HPC, but we will start adding courses about quantum computing in this autumn, I hope so. And yes, but we don't have a specific program for this.
I would say that, certainly the resources that we have at Oak Ridge, and it sounds like CINECA as well, are great places to kind of learn more about the technology. At Oak Ridge, we have something called Quantum Computing User Program that actually has access. You can get access to these quantum computers remotely in order to test out some ideas. It's very competitive and really intended for advanced researchers, but working with other researchers, this could be a good way to learn more. And then, of course, programs like Wiser, I think, are doing an amazing job in our community by exposing people to these remarkable ideas. And I know that we've been really happy to join you today and talk with you, Ricky, about everything that's going on.
The pleasure is honestly mine. Just hearing from you guys working on these problems is always super exciting. So yeah, thank you guys.